Hello and welcome to this presentation on spectroscopy. This is an introduction to spectroscopy. There will not be a lot of details, but you will learn a lot about three basic types of spectroscopy that you would probably see in a college level course. Now first off, what is spectroscopy? Well, with the prefix spect, we expect there to be something to do with light, and the scopy at the end. We expect we're going to be looking at something. And that's what we're doing. We're looking for phenomena that occur when electromagnetic radiation interacts with molecules. So we're going to be hitting molecules with different types of light, sometimes visible, very often invisible. In this case, it will all be invisible. And we're looking to see how the molecules react. Now, there's three types of light that we're going to be looking at in this presentation. Those are going to be X-rays, which are very energetic. X-rays are strong enough to knock off electrons from molecules, and that makes them positive ions. That's important, that they're going to make them positive ions. And sometimes those X-rays can actually break bonds. And when we break bonds in a molecule, that makes what we call fragments, and that's exactly what you think it would be. They're pieces of the molecule that break off and separate from the rest of the molecule. Now, infrared radiation, which is a lower energy radiation, definitely not strong enough to take electrons off or break bonds, but it is just the right energy to make bonds, which we can kind of imagine are like little springs with the attraction between the electrons and the nuclei in the middle. It makes the bonds bend and stretch back and forth. So infrared radiation makes the molecules kind of wiggle. And we can see that wiggling. And finally, radio waves, which are even less energetic. When hydrogens in the molecule are in one magnetic state and they relax to another, radio wave energy is given off. And radio wave energy can be absorbed when we go from one magnetic state to another too. And that's something we're going to talk about last, and we'll get to that. So the first thing we're going to look at is mass spectroscopy. In mass spectroscopy, we can see the apparatus here. What we're going to be doing is we're going to be taking a look, obviously, at the mass of the molecules. And we're going to inject the sample over here on this side on the left. And what we're going to do is we're going to vaporize it by heating it up so it's a gas. But then we're going to hit it with some high energy electrons, and those are our X-rays. And what that's going to do is it's going to cause an electron to get knocked off from the molecule, and all of a sudden the molecule is now going to be an ion. And sometimes the molecule actually breaks apart into little tiny pieces. Sometimes it does break apart and sometimes it doesn't. Either way, these newly formed ions, and don't forget they are now charged, move down this way in the mass spectrometer, and then they get to this magnet on this curve right here. And a magnetic field, especially a strong one like this in a mass spectrometer, has the ability to affect charged particles. So these are ions now because they've been ionized by the X-rays that are being passed through. And when they get to this magnet, they are deflected by the magnet. The magnet can actually change their path because now they're charged particles. The thing is, it's easier for them to change their path if they're lighter. So we could see this band right here. This is probably a relatively light molecule or piece of a molecule. Whereas if they are heavier and have more inertia, then it's harder for them to deflect, and we might get something that's over here. Now this detector here can tell when a fragment or a molecule hits it, and it records how many times it gets hit in which spot. And it knows that the heavier molecules are over here, and as we move this way across the detector, the molecules get lighter and lighter. So what it can do is it can tell us what the size of the molecules and pieces of those molecules are by ionizing them and then whipping them around a corner with this giant magnet and seeing where they land. The readout that we're going to see is this one here. It's got the mass down in the bottom, and it says M to Z for mass to charge ratio, but We can just think of that as mass, since the charge is always going to be 1, so the mass to charge ratio would be equal to 1. And the relative intensity here is going to tell us pretty much how often something of that size hits the detector. And we can see our values down here, 25, 50, 75, 100. And this spectrum right here has these signals right down here at the end. We can see these signals here, and we'll see an enlargement. Now, here's an enlargement of the end right there. We see this line right here that we call a signal, or sometimes we call it a peak, is right at 176. Right at 176. That's what we call our molecular ion peak. It's called molecular because it's the whole molecule. The heaviest thing that can come through the mass spectrometer is the molecule that hasn't broken up yet. And that's what we call the molecular ion peak. Any piece that's broken apart is obviously going to be lighter than the whole molecule. So if we want to find out what the molar mass of the molecule is, we look for the molecular ion peak, which is the farthest peak to the right, except for these little tiny peaks right after it that we call isotopic peaks. And we're going to ignore those. And the reason they're there is because not all of the carbon in the world is carbon-12. Some of the carbon in the world is carbon-13. And when a molecule happens to be made of an atom of carbon-13, with one of its atoms being carbon-13, it's going to weigh one more than we would expect. And that's what we see with this peak right here. And in this one, you can actually see just a little pixel here. That's a molecule that has probably 2 carbon-13s in it. Anyway, we're going to ignore these little peaks that are 1 unit after this taller peak right here. So we're always going to go the farthest peak to the right, but we're going to ignore these isotopic peaks. And the isotopic peaks you can see are much smaller than the molecular ion peak that we're looking at. So our molecular ion peak is right here at 176. So the molecule's got a molar mass of 176. Here we are back again at full size. So we can see where our molecular ion peak is there at 176. And the isotopic peak shortly thereafter that we're going to ignore. Now, we do get the molecular ion peak, but we are also going to get some fragments that come from the molecule breaking apart as it goes through the mass spectrometer. And here's what the rest of the spectrum looks like. Right, all these lines back here down on this end. Okay, all these lines down here. Some are high, some are not. These are all from fragments, from pieces of the molecule. And if we were going more into detail, we would care about them. But right now I'm going to tell you just to ignore all the fragments. We're not going to do anything with them. All we're going to look at on our mass spectrum is the molecular ion peak here so that we can get the molar mass of the molecule. Okay, so what you should do now is stop the video and take a look at the follow along document and open the exit questions and answer exit questions 1 through 3, which ask you about identifying the molar mass of compounds from their mass spectra. The video will begin again in just a few seconds, so pause now if you want to do the exit questions now. Okay, next type of spectroscopy, infrared spectroscopy. So like we said, this is a less energetic type of electromagnetic radiation. It is not going to be able to break bonds or knock off electrons, but like what we said, it's going to be able to make bonds in molecules bend and stretch. And like we said, if we treat these like little springs, we can make them wiggle back and forth. You know, they're not connected by sticks like the molecules that we build in class with the models. They actually have some give to them because it's just electrons and nuclei being attracted to each other. So we can make those bend and stretch if they absorb just the right frequency of light. They're quantized like anything else. So if it's not the right frequency, it's not going to make the bond bend and stretch. And different bonds have different frequencies. So we can tell what type of bond it is by what frequency of infrared radiation it will absorb. Now here's a good picture of kind of what it looks like. We're going to have our sample, right? and this isn't what the instrument looks like, but this is just a nice diagram, that we're going to run all these different types of infrared light through. Now, infrared light is a large band of the electromagnetic spectrum. There's lots of different frequencies within the infrared range. So here's a whole lot of them, and we're going to pass all of them through the sample. And then on the other side, we're going to look for all of those frequencies of infrared radiation that went through our sample. And we see a lot of them come out the other side with just as much radiation as they went in, which means that the sample did not absorb that radiation. There were no bonds in the molecule, apparently, that were just the right frequency in order to absorb that radiation and therefore make the bonds bend and stretch. And we see no absorption in these ranges either, but this red one, a lot of radiation went in to the sample, but very little of the radiation came out the other side. The remainder of it was absorbed. And our detector can tell that light was emitted over here, but it didn't see the same amount of light when it came out. And that's going to tell us that a molecule in our sample absorbed that very specific frequency of infrared radiation. Here's the output that we're going to see. Down here is wave number, which is related to the frequency of it, the wavelength of the light and the frequency. I'm not going to go into detail about what wave number actually is. We're just going to look at the scale and we'll use wave number, but it's related to the frequency of the light that's going through. So all of these would be different frequencies of infrared radiation. And here on the y-axis, we're going to see the percent transmittance. Okay, so if 100% transmittance, 100% transmittance would be if all of the light went through. That means nothing absorbed. 0% transmittance would mean all of the light was absorbed, as in none of the light of a particular frequency came out. And what we're going to be dealing with is stuff that's kind of in the middle. So if we see something where at a certain frequency the transmittance dips down a ways, that means that we're going to have a bond that is absorbing that frequency of energy, and that's going to be really important for us. So if we take a look at the signal from an actual molecule, an infrared spectrum looks something like this. And you can see it's quite complicated. But we see kind of our baseline up here, above 90% or so. This is where nothing's really absorbing, nothing's really absorbing, nothing's really absorbing, and then all of a sudden, here we go. One of the bonds in our molecule is absorbing a lot of infrared energy in this range, and the same thing here. And over here it gets really, really complicated. There's all sorts of signals and peaks over here. Now, anything to the right of 1500, that's an important point right there. Anything over here we're going to completely ignore. This is what's called the fingerprint region, and we are not going to get detailed enough to go into the fingerprint region and get any useful information out of it. So in this presentation, this introduction, we will never look at anything with a wave number less than 1500. So I'm going to keep it covered up right here. But things that are over here, these are going to become very important to us. We're going to have a list of what bonds absorb in what range, and that's going to tell us exactly what bonds are in a certain molecule. Now, here's a simplified table of 5 bonds that we commonly see in organic molecules. We've seen these in class multiple times. And it's the carbon-hydrogen bond. We see carbon-hydrogens all the time. The carbon double bond oxygen. We see carbon double bond oxygen quite often as well. Carbon-carbon double bonds. And 2 different types of OH bonds. OH bonds that we see in alcohols and OH bonds that we see in carboxylic acids. Now each one of them absorbs in a very specific range. And it will always be found in this range. And the intensity can be anywhere from weak, carbon-carbon double bonds are weak in their intensity, to strong, like a carbon-oxygen double bond. And these 2 down here are also very broad, whereas a lot of peaks are relatively narrow and they're in a very tight range. These can be very, very broad. They spread out for quite a ways, and they're pretty distinct because of that. So to look at a couple of molecules for an example, this molecule here we see is hexane, right? This is just a regular straight chain alkane. There's really not a heck of a lot going on in this molecule. There's no functional groups. Now we do not have the carbon-carbon single bond, signal in our chart. The carbon-carbon single bond is back in the fingerprint region, so we're not going to be looking at that. So the only thing that's important to us is the carbon-hydrogen single bond. And we see the carbon-hydrogen single bond absorbing in this range here, 2850 to 3000. And that's pretty much right where we're seeing all of this activity right here between 2850 and 3000. So whenever we see this, and since almost every molecule that we deal with has carbon-hydrogen bonds in it, we're going to know that this is a carbon-hydrogen bond. This is the signal that we see. Right? It's relatively narrow, it's very strong, goes down very far to nearly 0% transmittance, and it's right in the range that we expect it to see. We will see carbon-hydrogen bond signals in just about every molecule. Now here's an alcohol. This is ethanol. We still see the carbon-hydrogen bond signal. It's still there because alcohols have carbon-hydrogen bonds just like everything else. But now we also see this really broad, very, very deep, strong absorbance here in the range of 3400 to 3700, kind of in this range here. Now what's important is that the OH that we see in the alcohol is shifted to the left compared to the OH we see in carboxylic acids, and that creates this gap right here. And that's going to be something that makes it really easy to distinguish the alcohol OHs from the carboxylic acid OHs. The carboxylic acids are going to be shifted over to the right, and they're actually going to overlap with the carbon-hydrogen a little bit. So here we are in an alcohol where we have two interesting types of bonds, the carbon-hydrogen that we see here, that we've seen before, and now we have our new one, the OH in an alcohol. Here's an example of a carbonyl compound, carbon double bond oxygen. In this case here we have 2-hexanone. Now it would be the same if it was a ketone or an aldehyde, because both ketones and aldehydes have carbonyl groups, and we would see this in esters as well. But here we're taking a look at just a ketone or an aldehyde. This is a ketone. So we see our carbon-hydrogen again, right? It's the same signal right here from 2850 or so to 3000, same intensity. But now we see our carbon-oxygen double bond dipping right down here between 1710 and 1750. It's a very strong peak. It's usually very, very narrow. But what's important is that it points right down here, right at the correct spot on the axis. So this is 1500, 16, 1700. So it's just over 1700, right where we'd expect it. This is going to be our carbon-oxygen double bond. And it's very, very strong. The carbon-carbon double bond is very, very weak. They're in the same neighborhood. You can tell the difference. It's going to be over here, right, in the 1600s rather than the 1700s. But they are close, and sometimes they could be mistaken for each other. But the carbon-oxygen double bond is going to be very, very strong and very, very deep, whereas the carbon-carbon double bond is going to be pretty weak. We're going to see one of those in just a second. Now here we have a carboxylic acid. Now carboxylic acid actually has a couple of different functional groups that we can see, because besides the carbon hydrogens, which we always have, it's got a carbon-oxygen double bond. We see the carbon-oxygen double bond here right past 1700, just where we expect to see it. Nice strong signal. But it's also got an OH, which is like an alcohol, but this is a very different OH because of the different environment that it's in. This is an OH in a carboxylic acid, and it goes from 2800 to 3300 all the way across here. And we can see it overlaps with the carbon hydrogen. We can see the carbon hydrogen just kind of sticking out the bottom here. That's the bottom of the carbon hydrogen that we've been looking at. But now we've got this OH in carboxylic acids. And the big giveaway is that you've got this broad peak here, but you've also got the carbon double bond oxygen. And that's what's going to tell you that this is a carboxylic acid. So not only is it shifted over so that it's overlapping with the CH, it's also coming along with a C double bond O. Now if we go backwards and take a look at the alcohol, we're going to see that it's not overlapping, and this will completely disappear. So here's the carboxylic acid, which is one type of OH bond, and here's the alcohol. You can see that the carbonyl peak, the C double bond O, is missing, and there's this gap now between the OH and the CH. They're not overlapping each other. Here we are back at the carboxylic acid. Very, very different. And finally, here's an alkene, carbon-carbon double bond. Here's an example of the alkene carbon-carbon double bond peak. We can see it's very weak, doesn't stick down very far, and it is down here in the 1600s, not over in the 1700s, so it's definitely separate from the carbon-oxygen double bond. But the thing that makes it very distinctive is its weak intensity. And again, we see our CH bonds over here between 2850 and 3000 because we see carbon-hydrogen bonds all over the place in this alkene. But we do see the distinctive carbon-carbon double bond in this as well. At this point, you should be able to answer exit questions 4 through 6 in your exit question packet. The spectra that you need are in the follow-along document. Take a look at them. Answer the questions. If you need to, rewind the video and watch again. In a few seconds, the video will continue, so pause now if you need to. Our third and final type of spectroscopy is nuclear magnetic resonance spectroscopy, or what everyone calls NMR. Now the nuclear is referring to the nucleus of the hydrogen atom. We can do it with different atoms, nuclei, but we're going to specifically focus on hydrogen in this presentation. So the nuclear refers to the nucleus, and we're going to be dealing with the magnetic properties of the nucleus, the fact that it's got a quantum property called spin. Now, we have spin of the nuclei in these molecules, the hydrogen nuclei, and that spin, when a magnetic field is applied, this is an external magnetic field, like holding a magnet up to the molecule. When a magnetic field is applied, the spin of the hydrogen has to line up so that the magnetic field produced by the spinning hydrogen is exactly what the magnetic field is, or opposite. Those are the only two possibilities. If you were to take the magnetic field away, then these could actually point in any direction that they wanted to. The hydrogens could spin in any direction that they wanted to. But when the magnetic field is applied, they have to line up either what we call parallel in the same direction or anti-parallel. And that's what nuclear magnetic resonance spectroscopy is going to do. It's going to make use of a magnetic field, and it's going to take a look at these hydrogens as they line themselves up with the magnetic field that we apply. Now, the magnetic field that we apply and make these hydrogens line up parallel or anti-parallel, there is going to be a gap of energy between those. And that's what we're going to be looking at. The gap in energy between them can tell us what types of hydrogens they are, meaning kind of where in the molecule they are and what other atoms might be around. And this energy that's given off is in the radio wave frequency. Very, very, very low energy. But we can read that energy that's being given off when the magnetic field is being applied, and that will tell us something about the hydrogens. Now, the key to this is that the nucleus, which is what we're affecting with our magnetic field, is protected to a certain degree by the electrons around it, and we call that shielding. The electrons shield the nucleus from the full force of the magnetic field that's being applied. And given the fact that certain nuclei can have a more robust electron cloud around it, and some do not because maybe they have an electronegative element nearby, some hydrogen's electron clouds will be big, and that's very protective, shields it very well, and some hydrogens will have a very small electron cloud because their electron density has kind of been taken away from them, and that's not going to shield them nearly as well, and they'll be more exposed to the magnetic field. We're going to look at that on this axis here, where hydrogens that have a greater electron cloud around them, that have greater shielding, pardon the email notifications, that have greater shielding are going to show up to the right down here, and we call that upfield. Hydrogens that have maybe electronegative elements nearby or for some other reason have lost some of their electron cloud and have been de-shielded, that means taking their shielding away, not much shielding, they're going to end up down here on the left of the spectrum, and that's what we call downfield. Downfield meaning a weaker magnetic field could make them flip from one direction to another, and a stronger magnetic field or up field. Higher magnetic field will be necessary to flip them. These are well shielded, higher magnetic field needed, up field. These have less shielding, therefore a lower magnetic field or a down field. We'll be able to flip them from one spin state to another. Our reference standard that we run it against is called tetramethylsilane, and we always add a little bit of tetramethylsilane into the sample, and we set that equal to 0. That's because all of these hydrogens are identical. All of these hydrogens are attached to a carbon, which are attached to a silicon in the middle. So these hydrogens feel like they have the exact same environment as these hydrogens, and so do these, and so do these. And they're going to be very well shielded because since carbon has a higher electronegativity than silicon, electrons are kind of coming out this way towards the hydrogens and not away from them. So these hydrogens will have some of the fattest electron clouds that we could ever imagine. They're going to be very well shielded and should show up all the way upfield. And what we do is we put some of this into our sample and we look for this peak all the way to the right, and then we set that to 0. That's going to be way over here at 0. Okay, actually it should be at the 0, but for some reason it's not. So just imagine that at the 0. Okay, so let's take a look at one molecule here. This is our ethanal molecule. It's 2 carbon, it's an aldehyde. So the oxygen here is very, very key because oxygen has a very high electronegativity. And it's got some hydrogens here and this hydrogen here. Now, these 3 hydrogens are all identical to each other. All 3 of these hydrogens feel the exact same thing. They're connected to a carbon that's connected to another carbon that's connected to an oxygen, which is very electronegative. But this hydrogen would tell that same story, and so would this hydrogen, and so would this hydrogen. So all 3 of these hydrogens are identical. That's what we call one hydrogen environment. All 3 of these hydrogens are one environment. It's unique, but they're all the same within it. This hydrogen, though, would be different because it's closer to the oxygen. It's not separated from the oxygen by 2 carbons, but only 1. So this hydrogen is connected to a carbon that's directly connected to the oxygen. Therefore, the oxygen is going to do a better job stripping electrons away from this hydrogen than from these hydrogens right here. And what we see is we see different signals. Here's our TMS peak. That's our reference standard, so we can kind of ignore that. Whenever you see a peak right at 0, that's your tetramethylsilane standard. That's what we use to calibrate the instrument, and you can just kind of ignore it. But we see 2 signals, and the reason we see 2 signals is because we have 2 hydrogen environments, and one of them is going to have very light shielding because the oxygen has stripped the electrons away, and we see that peak way downfield. And here we're going to have much heavier shielding because the electronegative oxygen is farther away. These hydrogens retain more of their electron cloud that protects them from the magnetic field. Therefore, we're going to see them further upfield. A stronger magnetic field would be necessary. So when we look at this molecule, ethanal, with nuclear magnetic resonance spectroscopy, we can tell the difference between the hydrogens on this end of the molecule and the hydrogens on this end because they're in different electronic locations within the molecule. This is kind of a roadmap to tell you approximately where on this axis you'll see different types of hydrogens, and this is in your follow-along document. Way down here, very far upfield, near where we'll see our TMS peak very often. This is where we have our regular alkyl hydrogens. Hydrogens that are just attached to carbons and not much else. There's nothing electronegative nearby stealing their electrons. So those are some of the things that we see the farthest upfield. Whereas down here we see carboxylic acid hydrogens. Now we're not concerned about any of the other hydrogens in the molecule, just the hydrogen right here on the carboxylic acid itself. Now this is one of the lowest shielding environments that you could possibly have, to the point where it's acidic and it has so few electrons it can actually break that bond there and dissociate when it's in water. But this hydrogen has very low shielding, and we would see it way up here between 11 and 12, very far downfield. Here we see some aldehyde hydrogens, also very far downfield. We see benzene hydrogens kind of here in the middle. Here we see halogen hydrogens, right? Hydrogen on a carbon, also with a halogen on it, kind of in this range. We see alcohols and amines in this broad range here. So just like infrared spectroscopy, we can look at this and tell basically from where the signals are what type of hydrogen they are in the molecule. That's one thing that we can tell, and that's called chemical shift. This is a map of the chemical shifts of different hydrogens. It shifts one way or another depending on what type of environment that it's in. All right, now another thing that we can tell is how many hydrogens are being represented by a signal, because the more hydrogens there are representing a certain peak, that peak should be stronger. It should be louder because more hydrogens are giving off that energy. Here's a molecule that has different hydrogens represented with these different letters here, or labeled with these different letters. If we take a look through them, we see that there's some hydrogens here. These would be identical. Both these hydrogens would tell the exact same story about where they are in the molecule. They're hydrogens attached to a carbon that's attached to this carbon right here. And these hydrogens are attached to a carbon that are attached to this carbon right here. So even though they're on different carbons, they're completely symmetrical. Therefore, they're both part of the same hydrogen environment. There's nothing different about any of them that we would be able to tell with this spectroscopy. But this is a different part of the molecule. It wouldn't tell the same story. It's closer to this oxygen right here than the A hydrogens are. So that's going to be a different environment. D is closer still. Okay, D is going to be a different environment. And C is over on the other side. That's not going to be identical either. Even though this carbon and this carbon are the same distance from this oxygen, this carbon has a whole different thing going on over on this side. This carbon does not. So therefore C and D are going to be distinctive as well. So we can tell how many different environments there are. And if we look at this, and this is our TMS peak, our tetramethylsilane peak, we can see that we expect 1, 2, 3, 4 different environments, and we see 1, 2, 3, 4 environments here. But we can also take a look at the integration under the peaks. Now this is something that we would, if we wanted to do it ourselves, we would need some calculus for, but we need to get the area under each of these peaks. Luckily, computers do that for us, and that gives us a proportion of how many hydrogens are being represented. So if we take a look at what we expect here, we see how many hydrogens in this environment, and this environment, and this environment. We would take a look at these integrations, and we would expect to see 6 for the A hydrogens because they're represented by 6, 3 for the C, 3 for the B, right? We see 3 hydrogens here, 3 hydrogens here. These signals would each be half as strong as this one because this one's being represented, or is representing 6 hydrogens. And then finally, D only represents 2 hydrogens. That would not be as strong of a signal, and that would have an integration of 2. The integration is telling you how many hydrogens it's representing. Now, technically, the integration is only telling you the ratio of hydrogens, but in most of the simple molecules that we're going to look at, it is the actual number of hydrogens, not just the ratio of them. Sometimes it could be multiples of that ratio. So instead of maybe 6 to 3 to 3 to 2, maybe it was 12 to 6 to 6 to 4, which would be the same ratio, but it would just be a bigger molecule. We're going to be looking at these integrations pretty much as the number of hydrogens. Okay, one final thing we can tell, besides what type of hydrogen they are, and that's the chemical shift, and how many hydrogens there are, that's the integration, we can also tell how many neighboring hydrogens are nearby. That's by what's called the splitting of the peaks. The peaks themselves might not show up as just one single line. They might actually be split into multiple pieces. And that's because of hydrogens neighboring the hydrogens that we're looking at. Now that can get a little confusing, so let's take this pretty slowly here. Okay, so if we take a look at the blue hydrogen here, we see that the blue hydrogen is on this carbon. I don't care about any other hydrogens that might be on this carbon because those hydrogens would be the same. That's not what we're talking about. I'm not talking about hydrogens that are the same like we described before. I'm looking for hydrogens that are on an adjacent carbon. So not on this carbon, but I'm looking for hydrogens on this carbon right here. This is the neighboring carbon that we want to talk about, or the coupled carbon. Now since this hydrogen has no coupled hydrogens on a neighboring carbon, there's no splitting. Nothing happens to it. And therefore we see this signal as a singlet, right? A singlet, just one peak, there's no splitting, tells us that there are no hydrogens nearby. Now, if instead we had the blue hydrogen that we're looking at, we're still looking at the blue hydrogen with our NMR right now, but on an adjacent carbon, it's got one hydrogen. Now the thing that happens is the magnetic field of this hydrogen, which we said could either be parallel or anti-parallel, it's got two choices, right? Up or down. It could be the same as this one, or it could be opposite from this one. And that either helps or hurts this hydrogen in its attempt to kind of resist the magnetic field. And in a sample with millions and millions and millions of these molecules, there's going to be some blue hydrogens with a red hydrogen lined up with it, and there's going to be some blue hydrogens that have a hydrogen lined up against it. So therefore, when there's one coupled hydrogen, could be helping, could be hurting, what we see is what we call a doublet. It's centered on where we'd expect to see it, but we don't see a line in the middle. Instead, all we see is lines where the other hydrogen helped it, or a line where the other hydrogen hurt it. We're going to see one of these two. That's the only choice. You can either have your hydrogen being helped or being hurt. We're going to see a doublet. If we have two coupled hydrogens, we can expect what we're going to see. We're still looking at our blue hydrogen here, but now there are two neighbors, two neighboring hydrogens. And we're going to see a triplet. That's because either both of the red hydrogens could be helping, or both of the red hydrogens could be hurting, or one helps and one hurts, which is statistically twice as likely to happen, that there will be one in each direction. So if we have two coupled hydrogens, right, two neighbors, then we're going to have a triplet. And what we're building up here is what we call the n+1 rule. However many neighbors you have, you show up as a signal with one more, n+1. No coupled hydrogens, singlet, 0 + 1. One coupled hydrogen, you show up as a doublet, 1 + 1, 2. 2 + 1, 3. 3 + 1, 4, and so on. This would be a quartet. Now you can have more than that, because you could have carbon coming off the other side as well, and you could have multiple neighbors. But once we get above a quartet, usually it's just called a multiplet. Multiplet, meaning just many. They look like big squiggly lines. It's hard to even see them anyway. So if we get above a quartet, we're not even really going to worry about it too much. Okay, so here's a couple of examples. All right, here's one molecule. We have chloroethane here. There are two different hydrogen environments. These three hydrogens here, which are all identical to each other. And these two hydrogens here, which are all identical to each other, but they're different from these three, because they're a different distance from this electronegative chlorine here. So what we see is we see two signals. A signal over here that is split, and a signal over here that's split. Now if we look at the integration is given to you here, INT for integration. The integration for this signal is 2, showing it's this here, right, this signal, which we'd expect because these hydrogens are closer to the chlorine, so therefore we'd expect them further downfield. So here's your integration of 2. That must be a hydrogen environment with 2 hydrogens. This one has an integration of 3. Now notice it has nothing to do with the splitting. We're going to get to that in a second. But just because this is 3 and you see this split into a triplet, those have nothing to do with each other. This 3 means it represents 3 hydrogens. The fact that it's split into a triplet means it has 2 neighbors, right? So these 3 hydrogens right here, that's why it's got an integration of 3. But these hydrogens, which remember they are all the same, they kind of act as one hydrogen. These hydrogens have, if you go over here, 2 neighbors. 2 neighbors. And those neighbors could either both help, both hurt, or one help and one hurt, which is twice as likely. Which is why we see this peak right here from these hydrogens split into a triplet. It's got 2 neighbors and it's representing 3 hydrogens. Now we can see that those numbers don't correlate here because this is our integration of 2 further downfield. That's these hydrogens right here. But they've got three neighbors. These hydrogens, which are exactly the same as each other, have three neighboring hydrogens. 3 plus 1 is 4. That's why we see it split into a quartet. It's got an integration of 2, but it's a quartet. Those are different. The integration tells you how many hydrogens. The quartet tells you how many neighbors that it has. Here's another molecule, 2-butanone. We have hydrogens coming off from this carbon, and we have hydrogens coming off from this carbon and this carbon. You can kind of imagine how many there are. And they're all going to be different. These hydrogens that are coming off from this carbon are different in their relationship to this carbonyl group here than these, because this side has an extra carbon coming off, this side doesn't. Therefore, they're not symmetrical. They're not the same. This hydrogen environment will be different from this hydrogen environment. And this one's 2 carbons away from the carbonyl. This will be different too. Okay? So if we take a look at this, we can see we'd expect 3 different hydrogen environments, 3 different hydrogen environments, and we do see that. 1 environment, 2 environments, 3 environments. And we would expect to see integrations of 3 for the CH3 on the end, and another 3 for the CH3 here, and CH2 in the middle. So we do see our integrations of 3, 3, and 2. And as far as the splitting is concerned, these 3 have 2 neighbors. So the signal that I would see for these hydrogens should have an integration of 3, and with 2 neighbors it should be split into a triplet. And that's going to be this signal right here. Integration of 3 split into a triplet. It also makes sense that its chemical shift is so low. These hydrogens are the farthest away from this oxygen, so we'd expect to see them the furthest upfield. Now of the 2 that are next to the carbonyl group, we see these 2 hydrogens here, 2 hydrogens with 3 neighbors. That should give us an integration of 2, but a splitting of 4, right? So we see a quartet here. And this one, we see these 3 hydrogens, integration of 3, but notice there's no neighbors. This carbon doesn't have any hydrogens on it because it's bonded 4 times already. When we have no neighbors, we're going to be a singlet. Okay, so we're going to see a singlet here with integration of 3. That's these guys. We see a quartet with integration of 2. A quartet because it's got 3 neighbors. And finally, here we see a triplet. Why? Because it's got 2 neighbors right here, and it's a triplet with integration of 3. One final example. Here we see ethylbenzene. We do see the benzene hydrogens here, 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 and here, much farther downfield. Benzene hydrogens kind of show up down between 7 and 8 somewhere. So we can tell just by where they are on the axis that they are benzene hydrogens. We don't have to know anything special about it. We just look at our list of chemical shift values, and the only thing you're going to see between 7 and 8 like that is these benzene hydrogens. Now here we see the other signals coming from the CH2 and the CH3, and we see the integration of 2 here and the integration of 3 here. These benzene hydrogens, even though these 2 are different from these 2 and different from this one, the way benzene works, they all show up pretty much the same. They're not split up too much, and we really can't see the splitting here either. But we do see the integrations correctly. 3, 2, and 5. 1, 2, 3, 4, 5. Okay, now that should be enough for you to answer exit questions 7 through 9, which are on nuclear magnetic resonance spectroscopy. If you need to, go back and watch the video again. I'm going to stop for a minute. You can pause the video and answer the questions, and we will continue soon. We're almost at the end. Okay, so let's put it all together. Let's take a look and see if we can identify a molecule just by looking at the 3 types of spectroscopy that we've got. So we have no idea what a substance is. It's given to us, and we need to tell somebody what it is. So we're going to use our mass spectrometer, our infrared spectrophotometer, and our nuclear magnetic resonance spectrometer as well. Okay? So, the first thing we're going to do is we're going to take a look at the mass spectrum. And from this, we're going to get the molar mass of the compound. And I see here that the molar mass is going to come from the molecular ion peak here. I'm going to ignore the isotopic peak. And that's going to give me a molar mass of 86. So what I want to look for is molecules that would have a mass of 86. So I think to myself, well, what could have a mass of 86? You know, you can't have infinite carbons and hydrogens and oxygens. So lots of things could have a mass of 86. So I thought up for a few minutes what some of the examples would be, and I came up with these 9. And there's lots more. I actually searched things with molar mass 86 that are organic with just carbons and hydrogens and oxygens, and I found 61 independent isomers that you could make from carbons, hydrogens, and oxygens that would give this mass. Actually, a couple of them would have nitrogens in them too, but these are 9. We're just going to work with these 9. These will be our 9 molecules. There are others, but the molecule is not shown, or excuse me, the molecule is shown in these 9. So we don't need to worry about the rest. So what we're going to do is we're going to try and weed some of them out by looking at the infrared spectrum and the NMR spectrum. Right now, the mass spectrum tells us that all of these could be the molecule because all of these weigh 86. We have a ketone here. We have a ketone here. We have a branched ketone here. We have a diketone here, 2,3-dibutanone. Here we have an aldehyde with a carbon-carbon double bond in the middle. It's called crotonic acid, I believe. Here we have an aldehyde, just a regular straight chain aldehyde. There's pentanal. We have another aldehyde here. We have a branched one, right? We can have some branching in the chain as well. It doesn't have to be a straight chain. So we see an aldehyde with a branched chain. Here we have an alcohol with a carbon-carbon double bond as well. Okay, so this would be an alcohol. It's a different functional group along with the carbon-carbon double bond. Should be easy to spot. And then finally, here's another one that I thought of. We could do cyclopentanol, right? So we got 5 carbons in a ring, and we have an alcohol coming off from one of the carbons, cyclopentanol. So these are just 9 of the examples that we can make from something with molar mass 86. Okay, we're getting all of this from this peak right here at 86. That tells us the molecule in its entirety weighs 86. And these all weigh 86. All right, so let's look at the infrared spectrum. Now that's very distinctive because what we don't see is we don't see any large OH peaks over here, neither from alcohols that would be separate or carboxylic acids that would be overlapping it. Okay, we do see a carbon-hydrogen signal here, right where we expect to see it from 2800 to 3800, the carbon-hydrogen. We also don't see any carbon-carbon double bond in this area here. Sometimes these spectra actually are missing a piece there. It's not that they're trying to hide anything, it's just it didn't draw itself out there. But we're totally missing a carbon-carbon peak. So we do see here, though, a carbon double bond oxygen, right where we'd expect it, right past 1700. We could go check our sheet, and that would show us a carbon double bond oxygen. So it looks like we've got some carbon-hydrogen bonds and a carbon double bond oxygen, but none of these other bonds, which allows us to get rid of some of our molecules. Okay, there's no carbon-carbon double bonds, so I can get rid of that. I can also get rid of this. I can also get rid of this because there's no alcohols. Otherwise, we would have seen the large OH peak from 3300 to 3700 or so. And this is another alcohol. That's not it either. So it can't be a carbon-carbon double bond. I can get rid of that molecule, get rid of that molecule. And it's not an alcohol, so I can get rid of this molecule too. Which leaves me with some aldehydes and ketones up here. And maybe I'll be able to tell from the aldehydes and ketones from the NMR spectrum which aldehyde and ketone it is. Okay, so let's take a look at the NMR spectrum. And these are all in your follow-along document if you want to follow along with your own paper. So we take a look at the NMR spectrum, and we see 3 different signals. One here, one here, one here. But what I don't see is an aldehyde signal. Now if we look back at our map of where the chemical shifts are for hydrogen, aldehydes are very far downfield between 9 and 10, and I don't see any peak there. And since half the molecules that are remaining on my list are aldehydes, if it was an aldehyde, we should see a peak right here, and we don't. So since there's no peak here, there's no aldehyde hydrogen giving off that signal. And if there's no aldehydes, well, then I can get rid of a couple more. I can get rid of this aldehyde down here. I can get rid of the aldehyde over here as well. These were gone because there's no alcohols. This is gone because there's no double bonds. And that's leaving us down to 4 now. From 9, now we're down to 4. But if we look at the NMR again, we see that the integration of 6 and 3 and 1, well, that's going to tell us that there's one hydrogen environment with an integration of 6, another hydrogen environment with an integration of 3, and one hydrogen environment with an integration of 1. That should be pretty distinctive. 6, 3, and 1. And if we look at our molecules, there's only one that could give us a ratio of 6 and 3 and 1. And it's the one in the upper right-hand corner. This one here would have 1, 2, 3, 4, 5, 6. All of these hydrogens would be in the same environment. They're completely symmetrical. A hydrogen bonded to a carbon, bonded to this carbon here. A hydrogen bonded to this carbon, bonded to that carbon again. All of these hydrogens are in the exact same environment. But that's different than this hydrogen, and it's different than these 3 right here. 6, 3, and 1. It can't be these over here, because over here in this molecule, there is tons of symmetry in 3-pentanone. These carbons, these hydrogens here are exactly the same as these. It's a hydrogen on a carbon, 2 carbons away from the carbonyl group. A hydrogen on a carbon, 2 carbons away from a carbonyl group. Even though they're on opposite ends of the molecule, these are exactly the same. They're completely symmetrical. And these are completely symmetrical too, right? These hydrogens on a carbon directly next to the carbonyl carbon, hydrogen on a carbon directly next to the carbonyl carbon, there'd be lots of symmetry. We'd only see 2 signals, and we don't. This one here, the integration would be completely wrong. We'd expect to see 1, this one would be different, this one would be different, because even though they're both CH2, they're different distances away from the oxygen. We'd expect to see integrations of 3, 2, 2, and 3. This 3 different than this 3. And we don't see 3, 2, 2, 3. We see 6, 3, and 1. Therefore, it has to be this molecule. Of 61 possible isomers to begin with, we now have it narrowed down to the one structure that is shown by those spectra, 3-methyl-2-butanone. There's no other choice. The mass has to be correct. The types of bonds have to be correct that we see in the IR spectrum. And the number of hydrogen environments, along with how many hydrogens they represent, and as well the splitting, which we didn't really even need to talk about because we had already solved the problem. They all have to be just right. You can't have an NMR that has anything other than 6 to 3 to 1 for the integration. That is the conclusion of our introduction to spectroscopy. And there's one question left on your exit questions. And that is a mystery molecule for which you are given the mass spectrum and the IR and the NMR. And you need to analyze it just like we did the last molecule. You need to analyze it and find out what is that molecule. You look at the mass spectrum to get the mass. You look at the infrared spectrum to determine what types of bonds there are. And then you can look at the NMR to see how many different hydrogen environments and how many hydrogens are represented by each one. And you should be able to get to a definitive answer as to what is the molecule being shown in those spectra. That's the mystery molecule at the end, and that's exit question 10. I hope you've learned something from our introduction to spectroscopy. I will gladly answer any questions the next time that we have class, and enjoy the rest of your day.